If you truly understand the definitions of sine and cosine, you can, from that basic definition, deduce an incredibly large number of formulas and properties and rules and equations that are useful in all kinds of situations. Now today, you and I together are going to reason our way into several different properties of sine and cosine, just using the unit circle and using logic and using that original definition of sine and cosine. We're going to look at some special function notation that is used specifically for sine, cosine, and their powers. And then we're going to look at a very special and important identity called the Pythagorean identity. Now, when you're working with functions, we have function notation. Traditional function notation has the function's name, usually something like f or g or h, and then parentheses, and then inside of the parentheses is the input. Maybe you have f of x, maybe you have f of t, maybe you have g of a, anything like that. This is traditional function notation. And you might see it represented as maybe g of x with parentheses or brackets around it squared to represent g of x multiplied by itself. Now, sine and cosine are such frequently used functions that they have naturally evolved into some special function notation, which is a little bit different from tradition. The first thing that's special about sine and cosine is that often you will see them written without these parentheses around the input. So although it's traditional and technically speaking it's correct to write cosine parentheses 30 degrees, you might see this in practice actually written as cosine 30 degrees with no parentheses. Although it's technically only correct to write something like sine parentheses theta to indicate that theta is the input, you might also see this written as sine theta with no parentheses. So be on the lookout for that. Sine and cosine are used so often and are so special that they are sort of allowed this privilege of being able to walk around without their parentheses. The second thing that's kind of funky about sine and cosine, and a special privilege that they enjoy that other functions don't, is that the powers are written directly next to the name of the function, cos and sine. So if you see something like cos squared and then theta with no parentheses, this is the special notation for what would more traditionally be written as cosine parentheses theta parentheses with a square. Cosine of theta multiplied by cosine of theta. For example, if you were given cosine squared and then pi over 4, this is telling you to take cosine of pi over 4 and then square the output. Now from the unit circle, cosine of pi over 4 is the same thing as square root 2 divided by 2. So if I square that, then square root 2 squared is just 2. 2 squared is just 4. So cos squared pi over 4 would be the same thing as 1/2 in this notation. Regardless of what the variable name is that you're using, the quantity that goes into sine and cosine is always an angle. For example, if you're working with sine of t, then t is what is going into sine, so t represents an angle. Although theta is the most traditional way to represent an angle as a variable, other letters may also be used. No matter what it happens to be nicknamed, the quantity that comes out of the function sine is always, by definition, the same thing as the y-coordinate on the unit circle. So in this first example, this f of t would be equal to the y-coordinate on the unit circle, corresponding to the angle of t. Here in the second example, the input of sine is x. So even though it's called x, this quantity, which is inside of sine, has to be an angle in order for this expression to make sense. And the y, which is coming out of sine, would represent the y-coordinate on the unit circle, which corresponds to an angle which is equal to the input x. Now, where this sort of really gets frustrating is when you see expressions like the one in the third example, y equals cosine of x. No matter what, the quantity that comes out of cosine is the x-coordinate on the unit circle, even if for some reason someone has decided to call that output y. For example, here, the quantity that's going into cosine just so happens to be nicknamed x, but because it's going into cosine, we know that this x stands for a quantity which is equal to an angle. And even though somebody's bright idea was to call the output of cosine y, because it's the output of cosine, this y is equal to the x-coordinate on the unit circle, which corresponds to this input angle, in this case, which is nicknamed x. So do be on the lookout for that, regardless of the letter that somebody decides to use to nickname the input/output of sine/cosine. The input of sine and cosine is always an angle, and the output is always equal to the x-coordinate on the unit circle or the y-coordinate on the unit circle, depending on whether you're working with sine or cosine. Now that we've established that function notation with sine and cosine can get a little weird sometimes, let's practice looking at some properties of sine and cosine. Now, as we're going through these properties and writing them all down, I encourage you not just to memorize them. I think it is worthwhile to memorize all the properties described in this particular video, but I think memorizing them without taking the time to understand where these formulas come from isn't a very good idea. I think you should really pay attention to how we are getting these formulas. It will really help you to keep yourself from making mistakes. The first property that we observed yesterday is that if you have two angles which are coterminal, let's call them alpha and beta, then the sine and cosine values at those two angles are going to be exactly the same. Cosine of alpha is going to be the same thing as cosine of beta, and sine of alpha is going to be the same thing as sine of beta. Coterminal angles point to exactly the same direction, and therefore the coordinates at the point corresponding to that direction are going to be exactly equal. Now, because angles that are separated by 2 pi radians are coterminal, this is another way to put the result above. I could say that cosine of alpha plus 2 pi is the same thing as just cosine of alpha. If you increase an angle by 2 pi radians, then you're basically doing a full 360 and coming right back to where you started. Same thing is true for sine. Sine of alpha plus 2 pi is equal to just the same thing as sine of alpha. Nothing changes if you go one full revolution. Exercise. So suppose that you know that cosine of 12 degrees is equal to exactly this monstrosity. I won't even bother to read it, it's such a mess. Let's find the exact value of cosine of negative 348 degrees. Now, exact is a word that means that decimals are not allowed. So generally speaking, this is going to rule out the use of most calculators, because most calculators will give you an answer which is in decimals, and that's not allowed. Not when they say exact. Instead, let's try and use the property above, which is that two coterminal angles correspond to the same output values of cosine and sine. Now I can tell that these two angles are coterminal because if I look at the amount of separation between the two, if I take 12 and then separate out the negative 348 degrees, then I will get 360 degrees, which is one full revolution. So because negative 348 degrees and 12 degrees are coterminal, the output of cosine at those two locations is going to be exactly the same, which means that the output of cosine of negative 348 is going to be this monster, 1/8 negative 1 plus root 5 plus the square root of 6 times the quantity 5 plus root 5. Yeah. Let's see if we can find a relationship between angles that are not coterminal, but which are opposites. What happens if you plug in negative theta to sine instead of positive theta? Now, whenever you're working with a problem with sine and cosine, and you're not sure where to get started, I always recommend to start by considering the unit circle. Now, let me sketch just a random angle theta. Let's say theta ends up pointing in this location. What then would be the angle negative theta? Negative theta is going to give you the same amount of turning. It's just going to turn clockwise instead of counterclockwise. So negative theta is going to be the same angle. It's just going to point downward in this case instead of up. Now notice there is a rather conspicuous graphical relationship between the green point on the top here and the green point on the bottom. They're exact mirror images of each other across the x-axis. So because they're exact opposites vertically, the two y-coordinates are going to be exact opposites as well. The y-coordinates of the points corresponding to theta and minus theta are exact opposites. Because sine is what gives us the y-coordinates, that means that sine must be giving me opposite values as well. So in other words, sine of an opposite angle, sine of minus theta, which is pointing straight down, is going to give me the negative of sine of positive theta, which is pointing straight up. From this same picture, we can ask a similar question about cosine. Is there any relationship between cosine of negative theta and cosine of the positive version of that angle? Well, because these 2 points are vertically mirrored, the x-coordinates of those points are actually exactly the same. Because cosine is what gives us the x-coordinates of these locations. That means that cosine at these 2 angles is exactly the same. If I plug negative theta into cosine, I'll get exactly the same x-coordinate as if I plugged positive theta into cosine. Now, in the language of Pre-Calculus 1, we could say the following. We could say that sine is an odd function. Do you remember odd functions? Odd functions had this property that a horizontal flip, making the input negative, is equivalent to a vertical flip, which is making the outputs negative. In the language of Pre-Calc 1, we would say that cosine is an even function. An even functions had the property that if they were horizontally flipped by making the input negative, then the function didn't change at all. Nothing happened. So sine is odd and cosine is even. So let's use this property. We knew that cosine of 12 degrees was equal to this monster. Well, the opposite would be just equal to the exact same thing. Because cosine is an even function, so cos of negative 12 degrees is the same thing as cos of 12 degrees. This also gives you a fairly convenient way to find the value of something like cosine of negative pi over 3 without having to find a coterminal angle to negative pi over 3. We could say that cosine of negative pi over 3 is the same thing as cosine of positive pi over 3, and this is a value which does actually show up in our unit circle reference image. Cosine of pi over 3 is equal to 1/2, if I recall correctly. So that's another useful property of these formulas here. Another way to think about it, another example to show it, is if you wanted sine of negative pi over 4, then that's just the same thing as negative sine of pi over 4. And this angle here actually does show up in our reference image. Sine of pi over 4 is equal to root 2 over 2, and if I make that negative, then I have the value of sine of negative pi over 4. So that can save you some time. The last property of sine and cosine that I would like to take a look at today is something called the Pythagorean identity, which, as the name might suggest, is related to ye old Pythagorean theorem from back, I don't know when you learned it, whenever you learned Pythagorean theorem. Pythagorean theorem gave a relationship between the lengths of the sides of a right triangle. We had the length of the hypotenuse, which was the side that was opposite of the right angle, that was called C, and then we had the lengths of the 2 legs, which were called A and B. So with this notation, we had the formula that if you square A and you square B and you add those together, then that's the same thing that you would get if you squared C. Now, how is this related to what we've been doing with sine and cosine? To see the relationship, let's take our unit circle and let's draw a little right triangle in there. And I'm going to draw my hypotenuse from the origin. And notice that because the hypotenuse goes from the center of the circle to the rim, and because the unit circle has a radius of 1, that the hypotenuse must have a length that's also equal to 1. Now let's draw a line straight down and a line straight across. And having done this, we now have our right triangle. Now notice something interesting about the 2 legs of this triangle. The vertical leg, the length of the vertical leg, is going to be exactly the same length as the y-coordinate of this point here on the circle. So the vertical length of this triangle is going to be exactly the same thing as sine of whatever angle corresponds to this separation between positive x and the hypotenuse. Meanwhile, cosine is going to give us the horizontal leg. Cosine, the x-coordinate, is the same thing as the horizontal leg. So if I apply Pythagorean theorem to this particular right triangle drawn inside the unit circle, we get the almighty Pythagorean identity, one of the most important equations from this entire course. If we have any angle theta, then sine and cosine satisfy the following relationship. If I take cosine squared, that's our a squared, of theta, and if I add that to sine squared of the same angle theta, then the result of that is going to be equal to the hypotenuse squared, 1 squared, but that's just the same thing as 1. Notice that I'm using the alternative function notation for sine and cosine, no parentheses around theta, and the power is right next to the name of the function. Another thing that I want to point out is that whatever angle you're working with, the angle inside cosine and the angle inside sine have to be exactly the same for this to work. So, for example, if you are given an expression that looks like cosine squared of 17 degrees plus sine squared of 17 degrees, you don't even have to know what the individual values of cosine of 17 degrees and sine of 17 degrees are. Looking at this expression as a whole, we can see that it matches the format of the left-hand side of the Pythagorean identity. Cosine of some angle squared plus sine of the same angle squared. That can be immediately simplified. That's just equal to the number 1. But if you're working with sine and cosine and the angles are different, for example, cos squared of, let's say, 24 degrees plus sine squared of 24 radians, this is not equal to 1 because the angles are different. This is equal to some monstrous number, but you would probably need a calculator in order to figure out what value that was. As another non-example, if your cosine and sine don't have the squares, for example, if you had a cosine of, let's say pi over 4 as an example, plus sine of pi over 4, then this is not going to be equal to 1 either. You need the squares in order to use that identity. In fact, you can check using the unit circle that cosine of pi over 4 is equal to root 2 over 2. Sine of pi over 4 is the same thing. So if you add them together, you actually just get the square root of 2. You don't get 1 because you're missing those squares necessary to use the Pythagorean identity. So be on the lookout for that. In addition to giving us ways to simplify complicated expressions like this one, the Pythagorean identity can be used to get the value of sine from the value of cosine and vice versa. For example, suppose that we have an angle alpha, and we don't know exactly what the angle is, but it's pointing somewhere into quadrant number 1. So it's pointing somewhere into this location here, where both x and y are positive. Now we know that alpha is such that cosine evaluated at alpha is equal to 1 divided by 5. So let's try and figure out from that, what's the value of sine at the same angle? So let's figure out sine at the same angle using the Pythagorean identity, which contains sine and cosine with the same angle plugged in. Cos squared alpha plus sine squared alpha would be equivalent to 1. Now we know that cosine of alpha is 1 over 5. So if we square 1 over 5, that's going to be equal to cosine squared. So in other words, 1 over 25 plus sine squared of alpha is equal to 1. So if I isolate sine squared by doing 1 take away 1 over 25, we know that sine squared must be equal to 24 over 25. So now there are two possibilities. Possibility number 1 is that sine of alpha is equal to the square root of 24 divided by 25. Possibility number 2 is that sine of alpha is equal to negative square root 24 over 25. So which is the actual answer to this question? Is it the positive square root? Is it the negative square root? Is it somehow both? The answer to that question lies in this information about the quadrant corresponding to angle alpha. Angle alpha is pointing into quadrant 1, and everywhere in quadrant 1, y is positive. Because y is positive in quadrant 1, and the sign represents the y value, that means that the positive square root must be the answer, and the negative square root cannot be correct, because sine of alpha is equal to the y coordinate, which is positive in the first quadrant. Let's contrast that with the final example for today. We have an angle alpha, which is pointing into quadrant 4 this time, which satisfies the same condition, cosine of alpha is equal to 1 over 5. In quadrant number 4, the y values are all negative. So this is the problem where we would use the negative solution to the equation above. In this case, we would use sine alpha equals negative root 24 over 25. So to sum up, when you're working with an angle whose exact value is unknown, be careful when you're working with sine and cosine. It's worth remembering, hold on, I need life support. It's worth remembering that depending on the quadrant of the angle, sine and cosine will either be positive or negative. In quadrant number 1, x and y, sine and cosine are both greater than 0. In quadrant number 2, you're still above the x-axis, so the y is still positive. But this time you're on the left side, so the x is negative. In quad 3, all your cosines will be negative and all your sines will be negative. And in quadrant number 4, all your cosines will be positive, but your sines will be negative. That concludes today's material. We began by talking about the sort of special or strange function notation that's used when working with sine and cosine. Then we used the unit circle to look at a couple of different properties of sine and cosine, namely how they interacted with coterminal angles and how they interacted with opposite angles, theta and minus theta. Then we took a look at a very special property of angles, of sine and cosine, which is called the Pythagorean identity, which says that cosine squared of theta plus sine squared of theta is equal to 1. You can use this to do a couple of different things. You can use it to readily simplify some complicated expressions. As well, you can use it to find the value of sine from cos or the value of cos from sine. Just be careful to make sure that your answer is correct, either positive or negative, based on the quadrant into which your angle points.